So in this segment, we'll be talking about electrolytic cells. So these are the reverse, the opposite of a voltaic cell. Instead of generating electricity by having a spontaneous reaction, you apply voltage and make a reaction happen that otherwise wouldn't happen. To some sense, batteries rechargeable batteries are both voltaic cells and electrolytic cells because you run them in the reverse to make a reaction happen that wouldn't otherwise happen. So let's look at the specific lecture objectives of this segment. And so what the lecture objectives here are to label the parts and describe the behavior of an electrolytic cell and to predict which reactions will take place in an electrolytic cell. Okay, so the idea with electrolytic cells driving non-spontaneous reactions. In all these cells, so in all cells, whether voltaic or electrolytic, oxidation occurs at the anode and reduction occurs at the cathode. So that's the same, oxidation, anode, that doesn't change at all. So voltaic cells, the spontaneous reaction generates electricity. You are actually taking electrons from the electrode, and they're flowing downhill to the cathode to generate energy. And so the anode is the source of electrons. It has a minus charge. Cathode draws electrons and has a positive charge. In electrolytic cells, a non-spontaneous reaction is driven by an external electrical current. You're applying the current to force the electrons to go from the anode to the cathode when they really don't want to. Yes, the electrons are being pumped in the opposite direction. When we say the opposite direction that the chemical reaction would usually occur. We still call where the oxidation is occurring the anode. We still call what the cathode is, where the reduction is occurring the cathode, except that, before you might have zinc as the anode because and have zinc at the anode because the electrons are flowing downhill from the zinc, say, to the copper. In this case, if you were running it in reverse, zinc would be the cathode because you're actually getting reduction there instead of oxidation. So electrolysis is what we call these types of reactions, the process of using electrical current to drive a non-spontaneous reaction. It means electric, right? A lysis means breaking apart. So originally this came from the ideas that you had some compound and you would apply an electrical current and or electrical potential and run current and break that molecule apart. It can be used to drive all sorts of non-spontaneous reactions, but that's where the idea originally came from. And so that's why we use the name electrolytic cell, even if you're actually running some different reaction than just breaking a molecule into parts. So the most common type of electrolysis is, so electrolysis carried out in an electrolytic cell. The reason why they originally called electrolytic cells, it could be used to separate compounds into their elements. And a lot of times that was sort of the initial way that a lot of elements were recognized originally. You'd take some mixture and you'd run an electrical current through it and you'd get it to break up into compounds, either elements or much simpler compounds, and then you just cataloged those, figured out which ones of those you could break apart until people have identified most of the lighter main group elements, doing things like that. So in this case, we have electrolysis of water. You're applying an external current, and you need to have a little bit of salt in there because otherwise you don't get conduction of the electricity. But yeah, you get at the anode, you get water being oxidized and you get oxygen produced. And at the cathode, you get H2O, you get the hydrogen in water being reduced and you get hydrogen gas. At the anode, you get production of oxygen. At the cathode, you get production of hydrogen. And of course, you get twice as much hydrogen gas as oxygen. You can see right there, the stoichiometry. There's probably easier ways to get the stoichiometry, but it becomes very clear what the stoichiometry of water is because of that. So voltaic versus electrolytic cells, a lot of the setup is the same. Let's say we have zinc ions and zinc on one side and a voltaic cell, and the electrolytic cell, again, we have zinc and zinc ions on one and copper ions on the other. The difference would be on the voltaic cell, zinc is the anode because electrons like to go away from zinc. If we're applying the voltage, then the zinc electrode becomes the cathode. We're actually supplying electrons from to the solution, and so the zinc ions come out and come out of solution to meet those electrons, and we get we get the formation of zinc solid. And again, you have to pry the electrons away from the copper solid because really they'd rather be on the copper solid. But if you apply a voltage, you can pry them off. You can pull electrons from the anode, and once you pull the electrons from the anode, then the reaction becomes that you get the copper goes off into solution because it's had electrons pulled away from it. So that's the difference. If you look at what is the difference, which one is the cathode, is which one is the anode, the direction the electrons are flowing. But because the direction of the electrons are flowing is reversed, what was the cathode becomes the anode, what was the anode becomes the cathode. Okay. Electrons, but remember this, electrons still flow from anode to cathode. There's still oxidation at the anode, still reduction at the cathode. The opposite reaction occurs at each electrode than in the voltaic cell, setting up with the same half cells. Electrolytic cells, again, the electrons are drawn away from the anode by applying the voltage, which must be connected to the positive terminal to an external power source. So the anode is connected to the positive electrode of the power source. So electrons flow down to the positive source. So you've got an anode. The way you get the anode is oxidation. You get free electrons there. So those electrons flow down to the power source. So that's how you know in an electrolytic cell, the anode is connected to the positive terminal because electrons have to flow down to the positive terminal. So the electrons are forced to the cathode, which must be connected to the negative terminal of the power source. The cathode is to the negative because the electrons will then flow down from the negative terminal. The electrons will flow away from the negative terminal and into the cathode where reduction has occurred and electrons are gained during the reduction. So you can think of it as this way. So here we've got our electrolytic cell. The electrons are flowing from the anode to the power source, and you could they're flowing downhill to the power source. And then in the voltage source, they climb a ladder so they can flow back downhill to the cathode where the reduction is occurring. So they flow down from the anode. They get pushed back, so it's downhill there. The voltage boosts them up again, and then they flow back down to the cathode. So you could think of it, how do you get water to flow uphill? Well, it flows downhill till you get to some, water wheel that's pumping water up. It pulls it back up, and then it can flow down to the cathode. That's how you get water to flow downhill. You let it flow down a little bit, you pump it up, and then you let it flow down a little bit more to your final state, which is higher than your initial state. That is what the electrolytic cell is doing. So the electrons are always still flowing downhill, except at the voltage source. So the reaction that takes place obviously is the non-spontaneous process. You have to force that by allowing boosting the electrons back up in the voltage source. So of course, hydrogen plus oxygen is spontaneous. It goes to the free energy change is negative. There at spontaneous, the reverse process has to be have a free energy that's positive. The electrical energy is supplied by a direct current power supply, a battery or a DC power supply, and this is one important point that'll come up a couple times. Some electrolysis reactions, and it's really impossible to know beforehand because it has to do with exactly what's being oxidized or reduced and what the cell is, the electrode is as well, if you're using an inert electrode. They require more voltage than the E-cell predicts. This is called the overvoltage. And there's different sources for this. It could happen, maybe you get some coating when you run the reaction, you get a coating on the anode or the cathode, or because it's producing gas, you reduce the surface area. There's lots of weird things that can happen here and there. So you'd never really know beforehand, but you might have to, if the reaction you think should be happening is not happening, it might not be that you screwed up your calculation. It might be that you need an overvoltage in that particular case. So mixtures of ions undergoing electrolysis. So when more than one cation is present, the cation that is easiest to reduce will be reduced first. The least negative or the most positive reduction potential. And when more than one anion is present, the anion that is easiest to oxidize will be oxidized first at the anode. So if you have a mixture of things, you have to look and see what is the reaction that is the least non-spontaneous. that's the reaction that's going to occur preferentially. Even if you like supply a huge amount of voltage so that any of the reactions could occur, most of the reaction will be the easiest reaction to occur because that'll be the most spontaneous. And if you put enough energy, you can get multiple things to happen, but you won't get like the less favored one.